Thanks for watching this video. The paper I am presenting is titled Withholding Verifiable Information. In many economic interactions that involve communication between an informed party and an uninformed party, the communication messages from the informed party can be verifiable in that they can be vague, but can never be false. For example, think about the seller highlighting certain features of a product or advisors distilling market research reports for their managers. In these cases, if the informed party's messages are inherently false, it could face catastrophic consequences. Such communication settings are usually modeled as verifiable disclosure games in the literature. In these games, a sender who is the informed party privately observes a payoff-relevant state and then sends a message to the receiver, who is the uninformed party. Upon receiving this message, the receiver chooses an action that affects the sender's payoff. Verifiability is usually modeled as that the sender's messages must contain the true state. The literature in verifiable disclosure games primarily focuses on the receiver's preferred or the most informative equilibria. In fact, it is well known that under some conditions, there is an equilibrium in which the sender fully reveals her private information. However, little is known about how much can the sender benefit from verifiable communication. In particular, what does a sender's preferred equilibrium look like, and how well can sender do? Furthermore, what is the full range of the sender's equilibrium payoffs? I attempt to understand these questions in a very simple class of verifiable disclosure games. I find that there is a sender's preferred equilibrium in which the unpassed messages have a simple structure and can be interpreted as action recommendations. Moreover, there exists a continuum of equilibria with distinct outcomes satisfying the properties I just mentioned, which may suggest it might not always be appropriate to focus on fully revealing equilibria in policy debates. Finally, under some conditions, the sender can gain quite a bit from verifiable communication in general. Let me now jump into the model. There are two players, sender and receiver. The state space is the unit interval, and I denote a generic state by omega. Both parties share the common prior that the state is distributed according to a CDF F, which admits a strictly positive density. As previously mentioned, the sender privately observes the state and then sends a message to receiver. And observing the message, receiver forms an expected state based on it, which I denote by X. So I make three key assumptions. First, receiver has finitely many actions. For better intuition, in this talk, I assume that she only has 3 actions. So the action space contains only A0, A1, and A2. The results presented in this talk extend to finitely many actions in a natural way. Second, I assume that the receiver's optimal action only depends on the expected state. That is, there exist these cutoffs such that action AI is optimal if and only if the expected state is between gamma y and gamma I plus 1. You can think of the receiver wants to match the state and the action, but is constrained by the number of actions available to her. Finally, sender's payoff only depends on the receiver's action, but not the state. In jargon, she has state-independent preferences. In particular, she prefers a higher indexed action to a lower one. To illustrate the sender's payoff, it is useful to introduce sender's value function, which maps her highest attainable payoff as a function of the expected state. Because there are only 3 actions, the value function is just a 2-step function, as shown here. When the expected state is between 0 and gamma 1, receiver optimally plays action A0, and sender gets this payoff V of A0. When the expected state is between gamma 1 and gamma 2, receiver plays action A1, and this is what sender gets, and so on. Now let me formally introduce the notion of verifiability. I follow the seminal papers of Grossman and Milgram to assume that the sender's message space is the collection of all closed subsets of the unit interval that contain the true state. So every message is verifiable in that it contains the true state. The solution concept is perfect Bayesian equilibrium, where the first 2 bullet points are rather standard, and the third one is a consequence of verifiability. Finally, I define sender's preferred equilibria as the equilibria in which sender attains her highest or expected or ex ante payoff. To present the main results, I need to introduce some definitions first. I call a collection of 3 closed subsets of the state space, B0, B1, and B2, a partition if their union is the entire state space and the intersection of any of those 2 has measure 0. And an equilibrium is called an obedient recommendation equilibrium, or ORE, if there exists a partition such that for each I, for every state contained in partitional element Bi, sender uses Bi as her message. And upon receiving message Bi, receiver plays action AI. Therefore, every on-pass message Bi in an obedient recommendation equilibrium can be interpreted as a recommendation of action AI that receiver finds it optimal to follow. Note that I do allow for both sender and receiver to use mixed strategies. However, this class of equilibria is particularly simple because both parties play pure strategies. Now, the final definition before presenting the results. A partition is called obedient if for each of the partitional element Bi, the expected state upon receiving Bi is between gamma I and gamma I plus 1, and therefore action AI is indeed optimal for the receiver if she sees message Bi. In other words, Bi is indeed an action recommendation. And it is called incentive compatible, or IC, if in every state in Bi, sender prefers Bi to fully reveal the state by sending the singleton message omega. Assuming obedience, the left panel of the picture shows the IC partition. Why is that? Because in every state between 0 and gamma 1, if sender fully reveals the state, she gets action A0. And she gets at least A0 if she uses the corresponding partitional element as her message. In every state between gamma 1 and gamma 2, if sender fully reveals the state, she gets action A1, and she gets action A1 or A2 if she uses B1 or B2. If the state is above gamma 2, then sender gets action A2 to be played anyway. The partition in the right panel, however, is not incentive compatible. This is because in every state in the small red interval here, if sender fully reviews the state, she gets action A2, but she sends message B1, then action A1 is going to be played. Therefore, she may want to deviate to fully review the state if her state is in the small red interval here. Okay. However, in the left panel, she would always prefer to use these messages, the partition elements, than using fully review the state. My first result shows that a partition is the set of on-pass messages of an obedient recommendation equilibrium if and only if it is both obedient and incentive compatible. You may wonder, incentive compatibility only prevents deviations to fully revealing the state. But how about other deviations? I follow the literature to impose maximally skeptical beliefs. That is, upon seeing any off-pass message, the receiver would put probability 1 on the lowest state consistent with the message. Therefore, if the sender wishes to deviate, she can do no better than fully revealing the state. In this proposition, I show that there exists an obedient recommendation equilibrium that is a sender's preferred equilibrium in which the on-pass messages have a nested interval structure as shown here. So both B0 and B1 are intervals, and B2 is the union of at most 2 intervals, and it's basically sandwiches this B1. So note that both B0 and B1 can be empty. B2 cannot be empty because otherwise IC will be violated. However, it may be just 1 interval instead of 2. Furthermore, sender's expected payoff in this equilibrium is strictly higher than in any fully revealing equilibrium. The second part is relatively straightforward. Because there are finitely many actions, sender can take advantage of receiver's indifference through pooling. To establish the first part, the first step is to note that for every sender's preferred equilibrium, there exists an obedient recommendation equilibrium that gives the sender the same ex-ante payoff. This is done by using an argument closely related, although not exactly the same, to the revelation principle. Then I show that the nested interval structure is the most deviation-proof one in that the state in which lower actions are recommended are concentrated into an interval, which gives the sender the most leeway in choosing her favorite way of recommending actions. Going back to this example, in both panels, each action is recommended with the same probability, but the nested interval structure in the left panel make it IC, while the right panel is not without this nested interval structure. In fact, I can show that any payoff that is below sender's payoff in her preferred equilibrium and above her payoff in the fully revealing equilibrium can be sustained in an obedient recommendation equilibrium in which the on-pass messages have the same nested interval structure. This result shows that there is a continuum of equilibria with distinct payoffs in which both sender and receiver play pure strategies, and the on-pass messages take simple forms. This may suggest that in policy debates, focusing on the fully revealing equilibrium outcome need not always be appropriate. The last question I'd like to address in this talk is that how well sender can potentially do. Observe that an upper bound in the sender's ex-ante payoff is given by her ex-ante payoff when she can commit on what message to send in each of the states. In this case, sender essentially solves an information design problem. In the communication environment I study, these two nice papers show that the information design solution can be implemented by a partition such that it has this nested interval structure, and every partitional element recommends action AI. This partition is by definition or by construction obedient because every partitional element is an obedient action recommendation, and therefore it supports an obedient recommendation equilibrium if and only if it is also incentive compatible. That is, the sender never wants to deviate to fully revealing the state. Intuitively, when the sender can commit, she may recommend the middle action A1 too often or more frequently than incentive compatibility allows. This simple observation suggests an algorithm for finding a sender's preferred equilibrium. We can first solve the information design problem and see whether the resulting partition is incentive compatible. If yes, then we are done. Otherwise, we can obtain a sender's preferred equilibrium by making this B1 as large as incentive compatibility allows. The last result identifies a sufficient condition for attaining commitment payoff in an equilibrium. It says that if sender's payoff from action A2 is sufficiently high compared to her payoff from action A1, then the commitment payoff can be attained. The intuition is that when the payoff from recommending the highest action A2 is sufficiently large compared to the payoff from recommending the middle action A1, even if the sender can commit, she wouldn't recommend A1 too frequently. More generally, sender's value needs to increase sufficiently fast as the expected state increases. This result identifies a class of communication environments in which sender doesn't benefit from commitment power. For time's sake, let me skip the discussion and talk about the literature briefly. This paper belongs to the small literature on whether and to what extent the sender can benefit from verifiable communication. The most closely related paper is this one by Masha Titova, which studies a very similar model, but primarily focuses on the case of two actions. This paper is also related to the possibility and impossibility of attaining commitment outcomes in communication environments without commitment. Unlike the papers I listed here, which focus on cheap talk, this paper is about verifiable disclosure games. So to summarize, I explored the extent to which the sender can benefit from verifiable communication. I find that a sender's preferred equilibrium, I identify the sender's equilibrium payoff set. Each of these payoffs in the set can be attained in an equilibrium that the on-pass messages have a simple structure and can be interpreted as action recommendations. This may suggest that solely focusing on fully revealing equilibria in policy debates need not always be appropriate. I also identify a class of environments in which sender can attain her commitment payoff. And in these settings, the sender generically can gain quite a bit from verifiable communication. Finally, there are some applications that I have no time to cover today. Thank you for your attention. And if you have questions, please send me an email at the email address here. Thank you.